So then if I ask the question, what is the probability of A union B, right? Previously I said, assuming A and B mutually exclusive, it was probability of A plus probability of B, right? Now it turns out that I need to remove the part that gets counted twice. It is probability of A intersection B, right? This can be proved. Our textbook has a very simple 3-step proof of this. Since all these results are known, I'm not going to get into proof of this, right? But however, I urge you to go and read the textbook, chapter 5 of the book, right in the beginning, maybe second or third page of chapter 5. You can see a very simple and elegant proof of this, right? What is interesting from a communication point of view is what is called a conditional probability. Okay. I'm interested in asking the question, what is the probability of A given that event B has happened, right? So, A and B may have something in common, right? So, it is typically shown by a set, a Venn diagram. I have A and I have B, right? This stands for A and this stands for B. The fact that B has happened, meaning this entire event would have happened, right? And the fact that B has happened, I'm asking the question, does it mean some part of A has also happened, and what is the probability of that, right? So given that this is the common area between A and B, right, this means I have to first find out is a common area, that is A intersection B, and probability of B, right? So the conditional probability is defined as probability of A given that B has happened would be this small blue area divided by the entire area marked with red hashes, right? Of course, this assumes that probability of B is not equal to 0, right? If probability of B is equal to 0, then the event would not have happened at all, right? The fact that I'm claiming that the event B has happened means that it's an event of non-zero probability has happened, right? So this is a very important idea, that we'll keep using along with what is called the Bayes theorem in communication, right? So, and these conditional probabilities work exactly like ordinary probabilities, meaning I can ask the question, what is the probability of A union C given B, right? If A and C are mutually exclusive, this would be A given B plus probability of C given B, right? So conditional probabilities have all the properties of a probability, right? Everything that whatever we assign for probability, we can also assign it to conditional probability, right? This also has a sample space, this also has a probability measure, and there is a null set, there is an entire sample space, and so all those values can be assigned. So knowing this basic ideas, we can quickly come to a communication problem, a digital communication problem. So we are going to look at a binary communication problem. Meaning that I have a transmitter and I have a receiver, and there is a channel which I'm trying to model, right? As a transmitter, I'm interested in transmitting either a 0 or a 1. At any point in time, I have two symbols that I may be interested in transmitting, and at the receiver, I will receive a 0 or a 1. Okay. And on transmitting 0, right, with a certain probability, I will receive 1, right? Error. Okay. On transmitting 1 with a certain probability B, I will receive a 0. So 1 has been transmitted, but the receiver decodes it as 0. So that's an error situation. So A and B represents the crossover probabilities or error probabilities. On transmitting 0, most of the time, that is probability 1 minus A, I receive a 0, which is a healthy thing to happen, right? You transmit a 0, you expect to receive a 0. Similarly, on transmitting 1, you expect to see a 1 at the receiver, and that with a probability of 1 minus b. So this is the communication problem, or this is the model of a communication problem where we admit errors, right? We're not going to claim that our communication is an error-free process. So we model this problem by what is called an error channel or a binary channel. And if the crossover probability is A is equal to crossover probability B, then it is a symmetric channel, right? And so that is called a binary symmetric channel, meaning both the symbols 0 and 1 have identical probabilities of error. And it's called BSC. Okay. So we ask several questions, right? So suppose I ask the question, I'm standing at the receiver and I've received a 0, right? What is the probability of receiving a 0? Now I can get a 0 if a 0 is transmitted. I can get a 0 at the receiver even if 1 is transmitted, right? So we have now basic probability of transmitting 0 and 1. Let's call them as P and 1 minus P, right? Where P is the probability of transmitting a 0 or 0 being 0 showing up at the transmitter, right? So P is probability 0 is transmitted. Obviously 1 minus P is a probability that 1 is transmitted, right? So let's say P for some situation is 0.6 and 1 minus P is 0.4, So with the probability of 60% of the time I transmit only zeros, and 40% of the time I transmit only the other symbol 1. Okay. So given this situation, let's stick some transition probabilities, right? So let's say A equal to 0.1 and B equal to 0.25, right? So there is a certain error probability when 0 is transmitted. With the 10% of the time it appears as 1 to the receiver. When 1 is transmitted, 25% of the time it appears as 0 to the receiver. Okay, so let's now ask the question, what is the probability that 0 is received? Okay, like I said before, I can 0 is received, I'll use Rx when 0 is transmitted and the probability that 0 is transmitted. This is one event, right? This is one way I can receive a 0. Plus, there's another possibility, 0 is received when 1 is transmitted and probability that 1 is transmitted. So this now describes the complete possibility of receiving a 0. Okay, so I can now stick in the numbers. In the previous slide, I had assumed that the probability of transmitting a 0 is 0.6, right? So now we'll ask whether the probability of receiving a 0 also is 0.6 or it is something else, correct? So probability that 0 is received, 0 is transmitted is 0.9, because I assumed A is 0.1, right? In the previous page, if you see here, A is 0.1, meaning when 0 is transmitted, 90% of the time 0 is received, 10% of the time 1 is received, right? So this is 0.9, and probability that 0 is transmitted is 0.6, and probability that 0 is received when 1 is transmitted is 0.25, and probability that 1 is transmitted is 0.4. This is our assumption, right? So 9 into 6 is 54.54, and 25 into 4 is 0.1, and so this is 0.64, right? So I have a different number. To summarize, probability that 0 is transmitted was 0.6. However, probability that 0 is received is 0.64, right? So you see that the two probabilities can be different, right? So because the way the bits are transmitted in the channel, noise is added, and we may make an error. Okay, and all that is captured in these two statements. And the first of the two probabilities, that probability of 0 is transmitted, is what is called the prior probability, right? I mean, sorry, this is something that we know. This is something that we know, right? Beforehand. This is something that we know a priori. So the probability of 0 at the transmitter is the prior probability. Now, probability of 0 at the receiver is, now that I've received 0, right? So I'm asking this question, right? What is the probability of receiving a 0? This is what is called the posterior probability, or after the event, posterior probability, right? So we can have both prior and posterior probabilities, and the two can be very, very different. Okay, and the two can also be similar, meaning if there is an error-free channel, then whatever is transmitted is the same thing is received. I mean, imagine a situation like this where these crossover terms are missing, right? So you transmit 0, you receive 0, you transmit 1 and you receive 1. So in a situation like this, there is no possibility of error. So in which case the prior probability will be identical to posterior probabilities. But most of the time that won't be the situation. The prior and the posterior can be very different, right? Now let me ask you this question. Probability that 1 is transmitted in our situation is 0.4, right? Now tell me, what is the probability that 1 is received? Someone? Okay. Okay. So can somebody tell me what is the probability that 1 is received?
It's 0.36.
Okay, so it's 0.36, and so it's nice that the numbers are different, and there's many ways of looking at this. We know that probability of A is 1 minus probability of uh, a complement, right? And I also said that the conditional probabilities are treated as any other probabilities, right? And so it's these probabilities, we can simply apply the relationship that these probabilities also follow all the laws of probability. So if probability that 0 is received is 0.64, probability that 1 is received, given that that's the only other possibility, it has to be 1 minus that. Okay, so then we have what is called the Bayes rule, right? So the conditional probability I had was probability of A given B we said is probability of A intersection B by probability of B, right? Then similarly, probability of B given A would be probability of A intersection B by probability of A. Okay. So if you see the two formulas, it's clear that probability of A intersection B can be written as probability of A given B into probability of B, or probability of B given A into probability of A. Right? So the two are equal. Okay. So I can write probability of A given B, by rearranging probability of B given A, probability of A by probability of B. Okay, so this is a famous relationship called the Bayes relationship that connects the posterior probability of A to the prior probability of A. Okay, and given all the situations, it turns out that in many cases we know the prior probability and we're trying to compute the posterior probability, right? If you have all the okay, oh, 1 second please, let me take this phone. Yeah, hello Andrew. Okay. Yep. Sorry about this. Right. This was an important call connected with what we are trying to do. Right. So one last idea before maybe I can apply this to a situation again from communication. So we are back to the same communication problem. Right. So I now ask the question. Right. So given that I've received a 0, what is the probability that 0 is transmitted given that I've received a 0? Right? In this case, okay, in this problem, right, I'm standing at the receiver, and I've received a 0. Right? I'm asking this question, given that I've received a 0, what is the probability that a 0 was transmitted? Okay. Sometimes Bayesian answers are counterintuitive, right? I mean, if you're standing at 0 here, um, and a simple answer that somebody may want to give is something like 1 minus A or something like that, right? A is assuming A and B are known. Since I've received a 0, 0 must have been transmitted with a probability of 1 minus A. So let's see what happens if I apply this to my the Bayes formula, right? So it says here probability of A given B is probability of B given A and probability of A. So I say probability that 0 is received given that 0 is transmitted into probability that 0 is transmitted and probability that B is 0 is received. Okay. So I've just applied the Bayes formula for this. Let's see if I have answers to each one of them, right? So let me take this factor first, then this factor, then the one in the denominator, and we can close a lecture today with that, right? So it says probability that 0 is received given that 0 is transmitted? Okay, so ask me, tell me, what is this question? What is the probability that 0 is received given that 0 is transmitted? Somebody? 1 minus a, and a is 0.1, right? So if 0 is transmitted, the probability that 0 is received is 0.9. Is that okay? Then second factor is 0 is transmitted, this is 0.6, right? Now the question is probability that 0 is received, right? This we answered before, means probability that 0 is received given that 0 is transmitted into probability that 0 is transmitted plus probability that 0 is received given that 1 is transmitted into probability that 1 is transmitted, right? And that becomes 0 received, 0 transmitted is 0.9 into 0.6 plus 1 is transmitted, 0 is received, 1 is transmitted, 0 is received is b is 0.25, 0.25 into 0.4, this was taken to be 0.64, right? And so if you substitute here, this is 0.9, this is 0.6, and this is 0.64, right? And so I have 0.9 into 0.6, 0.64, and so this is 9 into 6 is 54 by 64, that is 27 by 32. Okay, so this is a very high probability. So what it means is, if you receive a 0 and ask the question what is the probability that 0 is transmitted, that probability is not equal to 0.9, that is 1 minus a. That probability is not equal to 1, but that probability is, for the numbers we have shown, that probability is 27 by 32, right? You can now ask the question, what is the probability that 1 is transmitted given that 0 is received? What will be the answer to this? Now I'm asking, I'm standing at the receiver, I've received a 0, right? I now ask the question, what is the probability that 1 is transmitted? So it is simply 1 minus 27 by 32, that is like 5 by 32, right? And you can continue this process. You can now ask the probability, what is the probability that 1 is transmitted given that 1 is received, and so on. And what is the probability that 0 is transmitted given that 1 is received, right? So you can find these two probabilities. So and so that's from the communication point of view, right? We are trying to find out, we are trying to ask such questions. Standing at the receiver, I've received something. I want to know whether the same symbol was transmitted or the same symbol was received, right? So I want you to find out now. Go back and answer these two questions, right? What is the probability of 1 being transmitted or 0 being transmitted when 1 is received? Okay, so two ideas that I've used. One of them is what is called the total law of probability. Total law of probability that says an event A, right, may not be observed of its own, right? Some A is observed when B1 event B1 happens. A is again observed when event B2 happens, and so on up to Bn, right? So probability of A will be probability of A given B1 into probability of B1, right, plus probability of A given B2 into probability of B2, and so on up to the last of the systems, right? Bn given probability of Bn, right? This is the total law of probability where an event A is not perceived independently, but it's kind of seen by its manifestation. If B1 happens, then A would have happened. If B2 happens, then A would have happened, and so on. So the total law of probability says you collect all these probabilities of these small events happening. From there, try to figure out the probability that A has happened or not. Right? That's one aspect of probability. A very important idea that we'll use is what is called independence of events A and B. Right? If A and B are independent, or they are said to be independent if probability of A intersection B, correct, is probability of A into probability of B. Okay. Then A and B are said to be independent events. Right? What this means is, if you ask the question probability of A given B, since A and B are independent, right, and A given B was defined as probability of A intersection B by probability of B, knowing B, I don't know anything about A. It doesn't give me any additional information. So this will be equal to probability of A if A and B are independent. Okay, so this is the review of probability. Uh, when we meet next, whenever it is, I'll send you a message. We will then go to the next topic of random variables. Right. Um, if you have any questions, you can ask now, because I have only a couple of more minutes left. Okay. So please ask me questions. If you have anything, or you can also send me email to seek clarification. Next time when you come, and if you continue to use this medium, okay. So yeah, uh, Amrita Varshini, you can you mute your mic? Yeah, okay. Thank you. Okay. So next time, if you continue to use this medium, then I expect all of you to come at the right time. Today, people kept joining until it's very late. I will also try to find out if there is a mechanism where the access control can be given to the TA, and TA can allow each student to join the session. Today, I was doing both. I was lecturing as well as doing access control. So my attention was divided. Whenever somebody comes and there's a bong sound, and I had to connect to it. So next time, when if we continue to stay with this medium, I expect all of you to join at the right time, right? Not after 10 minutes, not after 15 minutes, and so on, right? That's very important. Otherwise, our experiment will not work. Okay. So if you have any message, if you want to convey anything to me, send me email, or if you have any question, you can ask now. Otherwise, in another 2 or 3 minutes, we'll close the session. Okay. If you want to ask a question, please unmute and then ask. Okay. I see that there are some messages waiting here. I still haven't figured out how to read the message. Okay. Yeah. Anirudh Reddy says nice. I don't know. He's saying nice to what? And Sai Venkat Kushal had just there's no message from him. He says 0.36. So he has given the answer. Oh, okay, fine, excellent. Okay. I didn't know how to see all this, right? I think people, when I asked the question, I think some people type their answer. So very nice. I know this is new to me, so I wasn't looking at so many things. Okay, anyway, thank you. So we close today. Send me an email with your feelings about what happened in this class. Was it good, bad? All kinds of feedback. Okay. Yes. Bye. Okay.